Three-phase transformers. Now remember, whenever we're working with a three-phase system, we need to remember that the three-phase system can be connected in either star or delta configuration. And as a result, the work we've done on the three-phase star and delta, specifically the calculations, we need to incorporate that or remember that with these. Now when we look at the actual three-phase transformer, ignore the three phases for a second. We're just going to look at a single phase, and we can see that we've got one coil that is magnetically connected to a second coil. Let's call this our red phase. Now with our red phase, as we supply our voltage on the input, this will allow a current to flow through my primary coils. This current will create a magnetic field which will influence and induce a voltage into the secondary coil, and as a result, if this circuit is closed, we will have current, and as a result we will have our 180 degree phase shift that we learnt about in grade 9. So this is simple in the sense that voltage generates a current, the current generates a magnetic field, and that magnetic field generates a voltage. Now we have to remember that if the circuit is closed, we're going to have a current flow in this circuit as well. As a result, it's going to generate its own magnetic fields, which in turn is going to influence the magnetic fields on the primary. So that is my red phase. My second phase, the yellow is not going to show very nicely, is basically going to do exactly the same, but because my second phase is at 120 degree phase shift to my first phase, I will have a signal that looks like that, and as my output I will have a signal that looks like, also my sine wave, but with plus 120 degrees. My third phase, which is my blue phase, will do the following. I'll have my primary turns and my secondary turns, and these will, again, I will have my sine wave with a 120 degree phase shift over there, and as a result I will have that on my output. All three transformers work exactly the same. The only difference between these three is when their sine waves actually start due to the phase shift of the signal. Each coil will influence the other one with respect to current and voltage that's flowing, and each one will then develop its 180 degree phase shift with reference to that phase's primary. If we were to combine these three signals, I will see that on my red phase I will have a pure sine wave that starts at 0 degrees and ends at 360 degrees. My yellow phase, which is 120 degree phase shift, we will see starts approximately there, and it ends approximately there, and then my blue phase, or my third phase, will start over there, it'll go down over there. No, hang on a second, that's wrong. Should start about there, and then it should end about there, with my three at 120 degree phase shifts to each other. as you learned with generators as well as last year, that circuits or devices do not run at 100% efficiency due to losses. Now if we look at our transformer, go back. Now, when we're looking at this, we need to remember that although we're working with 3 phases, and irrespective of whether these transformers or these coils on the primary and secondary are connected in delta or star configuration, we need to remember that this is the phase voltage that affects this phase voltage. As a result, this phase current is going to affect this phase current. So when we work with ratio calculations, we need to remember that the phase values must be used and not the line values. Now looking at a transformer, we will know about the losses that can occur. These losses are due to a number of factors. The first loss we call our copper loss. This copper loss is due to the actual material that we use to generate the coils. This copper loss will generate unwanted heat, and that heat in turn will generate an increase in the resistance, which in turn influences the efficiency. The next aspect that influences the efficiency is my core losses. Being a soft iron core, this core will allow for losses. Core losses are also called iron losses. Okay, so basically what happens there is my iron losses refers to eddy currents that is created inside the core. Those eddy currents will again influence the temperature of the transformer, thereby increasing the resistance of the coils and thereby decreasing the efficiency. The third type of loss that is obvious are called the field leaks. Alright, field losses or field leaks. Okay, this is caused by when current flows through the coil, that coil will generate the magnetic field. But now if there's excessive current, then the core isn't going to conduct all the magnetic field. So as a result, my coupling coefficient in other words, the amount of magnetic flux that influences both coils will decrease. And because there's less flux cutting through both coils, we will have less voltage induced, and that will in turn decrease the amount of voltage that is induced.